All right, hello everyone. Looks like people are still trickling in. We'll go ahead and get started because we're at 11:45 on the dot. I'm curious, has anyone found any good Pokemon in this room? If you find anything interesting around the stage area, let me know so I can pause and catch it, because it's clearly my priority today. But hey guys, I'm Brandon Chavis. I'm a solutions architect on the partner team at AWS. And I generally focus on the Docker ecosystem, which means working with partners that build solutions that work with Docker, and making sure they work well on top of the AWS platform. So I think it's kind of good to level set at the beginning here, talk about an agenda. If you parse this talk title as just getting started with Docker, you might be a little bit disappointed. I'm not going to cover too much about the basics of like the Docker command line, for example, or the Docker toolset. And I also think that calling this getting started with Docker on AWS is a little bit broad because there's many, many ways to run Docker on AWS, and that might be with an AWS-produced solution, so like Elastic Beanstalk or Amazon ECS, or it might be with one of those partner solutions like DCOS from Mesosphere or Docker Data Center from Docker themselves. And we work with these companies to make sure all these things work really well on the platform. But today we're really going to talk about Amazon ECS in detail, which is what we've built for managing containers at scale on AWS. And we'll talk a little bit about how to use Docker with ECS. And so we'll talk about some of the core concepts here, and then we'll wrap it all up with a demo at the very end and kind of show going from just a Docker file in an application to pushing a container to ECR, which is EC2 Container Registry. And then we will kind of build a service and then do some rolling updates of that code while it's running in production here. So first of all, if you're not familiar with Docker, actually, a little bit of audience involvement here. Who is completely unfamiliar with Docker at this point? Who is completely new? So a couple of people, that's awesome. Who's already played with Docker a little bit? Probably about half. And then who are the unicorns out there running Docker in production? So we have a couple of those too. Awesome. So that's a great gradient. Very diverse audience, so that's awesome. I hope everyone can get a little bit out of this. But why containers? Some of you don't need to understand this, but I think personally it lets us care a lot less about things like operating systems or physical machines, and instead really focus on kind of the development workflow, which can be really valuable for just focusing on your core competencies, so focusing on your business or your application. So let's talk a little bit about how they enable that. So underneath your favorite container runtime, generally there lies a set of specifications that have been defined by what's called the Open Container Initiative. And those specifications exist in code form in a library called runc. And so runc more or less provides an API for hooking into and aggregating all of the underlying Linux kernel features that provide all that process isolation that makes up what we know as a container. So some of those things might be C groups, control groups, which allow you to do things like limit resource utilization for a particular process. Or things like namespaces, which provide the actual process isolation, so preventing one process from seeing another, preventing that process from seeing parts of the file system you don't want it to see. Any fans of the operating system Plan 9 by Bell Labs? Anyone remember that? Oh man, that's where the concept of namespaces originally came from, so thanks Bell Labs, that's awesome. But anyway, so all this stuff underneath, pretty useful concept. It basically lets you use the OS kernel to create multiple isolated user space processes that can have constraints on them, right? And so then on top of all these layers of abstraction sits Docker, which is a wonderful and user-friendly set of tools and workflows. They allow you to do things like build images, interact with containers, build and share, and build deployment workflows on top of those images, and really make all these things useful to the average developer instead of having to know a bunch of arcane components in the Linux kernel, which is great. So there's a few huge benefits to containers that we like to talk about mostly here at AWS. The first is that portability, and that is because the image that you build is consistent and immutable. And so that means that no matter where I run it or when I start it, I can run it on this laptop here, or I can run it in AWS in the cloud, and ideally the expectation is that the behavior is the same. And that's great if I want to run one here or if I want to scale it in production tomorrow, right? So there's less surprises. Containers are also flexible, and by that we mean that it makes it easier to decompose an application into smaller chunks or individual processes all running on the same host. But you can still do that while preventing like library conflicts. You can isolate those processes. So that streamlines code deployment and development, and also infrastructure management in many cases. And then they're also fast in that they bring speed advantages to your organization in terms of both like development and deployment workflows. So each container can be a single-threaded development stream, and your development teams can work on these individual processes and not worry so much about what their changes are doing to other code bases and other containers. And it can also benefit your ops teams because they're free to update base containers that your development teams can build on top of and not worry about having to take a machine down for updates or something like that. And so finally, efficiency. You can get a degree of efficiency from containers by specifically allocating CPU and memory resources to a given container and kind of chopping up your compute resources in a way that's most appropriate for your application. And it's a little bit more efficient than virtual machines in the sense that you can kind of cut out some of that OS overhead, and you don't have to run a single process per virtual machine. So with all these attributes, we're kind of watching containerization have pretty significant impacts on the architecture patterns we're using for building web applications today. And we see this with things like 12-factor applications, a real focus on like small, easily decomposable and deployable services instead of large monolithic applications. And so this is actually essentially what Amazon.com did many years ago. So they moved from a large monolithic code base, which was like one large application, the UI, the ordering, the recommendation systems, all of that was like one code base. And so that became kind of cumbersome. There was a lot of interdependencies between all the code here. Certain parts of the application maybe required more resources than others. And that was difficult to scale efficiently and get good resource utilization across the server fleet. So in order to scale better, Amazon decomposed its architecture and its application into a bunch of individual services that could be scaled easier. And it also allowed development teams to move faster because they could work on updates that could be delivered independently of the entire application being redeployed. So we would call this style probably microservices today. And we find that containers kind of really reinforce the patterns of the microservices architecture. The reason that they're so natural, there's a couple of attributes that make them so natural. And one of it is the ease of modeling services, right? So the application, all of its dependencies, they're all packaged together into a single artifact, into a single image with a Docker file. And that Docker image can support any app, any language, right? And the image itself is a versioned artifact that can be stored in a repository just like your source code. And I think that makes applications easier to deploy because that image is your deployment artifact also. So it can simplify your deployment because containers also really encourage stateless application design. And that means that that kind of decreases the risk of change because when you're deploying a new version, all the containers you're deploying are kind of just a new set of containers. So kind of all these things together kind of make it easier to decompose applications into microservices. This is a dumb slide. I don't know who has to block out lunch when the most strenuous thing on their day is picking up dry cleaning, but blocking out lunch is a pro move, and I respect that. But let's talk about scheduling in the context of containers. So basically, scheduling means that you need to get your app to the compute resources that are available to run them, very simply, right? So it's really easy to deploy a single container, maybe to my laptop right here, because I can just look at the resources I have available. I can check and see if that process is running very easily. But once I get to a situation where I have a lot of machines, a lot of containers, that probably means I'm managing a cluster. And that's not always a trivial task, right? We think that can be kind of a hard thing. So that's hard because you need a way of like intelligently placing containers across your whole fleet. And to do that, you need to know the state of everything that's in that cluster. So for example, which instances in this fleet have available resources for the given workload I want to deploy? So how do I know if it has memory or CPU or ports? How can I keep track of all the containers I've already deployed across this fleet? How do I know if they're running or if they've died or something like that? And then how do I make modifications across the whole fleet? If I want to roll out a new set of containers across 100 new nodes, that can be a little bit difficult to do manually, to say the least. So these are some things we hope to address with EC2 Container Service. So let's talk real quickly about what I think is the core competency of Amazon ECS. So it's a managed cluster manager service. And And that's significant because it's actually the way that we think about cluster management internally at Amazon. And we've kind of exposed some of these primitives to you through Amazon ECS and through the APIs. So let's talk a little bit about how it actually works. So first, we have a resource manager on the back end, and it's responsible for managing resources, so keeping track of resources across your fleet. So those resources can be memory, CPU, ports, and basically the availability of those resources at any given time. So is my instance healthy? Is it available to take new work? And then also there's a scheduler, which is responsible for scheduling containers for execution. So the scheduler contains some algorithms to assign tasks to the nodes in the cluster based on the attributes of your workload. So can this container, or can this instance handle an additional container with these requirements that it needs to run? So in order to do this, to schedule properly, you have to know your requirements for a given workload. You have to find a space, some resources on your cluster that meet those requirements. You have to request that resource and then confirm that it's yours, so there's no conflict on the back end for who actually owns those resources at any given time. And so we also think that a scheduler should have oversight over your workload's lifecycle. Is it running? Did it complete? Did it die? Should I reschedule it? Should I make sure it's running somewhere else? And you put these two things together, resource management and scheduling, and together they kind of provide the core functionality you need for cluster management at scale. So the cluster management engine aggregates the resources of multiple EC2 instances, and it just represents them all as a pool of CPU, memory, and ports, basically. The instances that run in ECS are just EC2 instances with a few little modifications to it. They run in your account, and they have an additional daemon running on them to help them communicate with ECS. But you own those instances. You can SSH into them. You can control the way that they're configured in a VPC. You have a lot of control over how they're actually configured. You can run whatever OS you want, although we do pre-build Amazon Linux for running with ECS, as do some other OS vendors. But this cluster also is dynamically scalable, so you can have a single instance cluster. You can have a 1,000 instance cluster. ECS really doesn't care about that too much. So on each instance, as I mentioned, we have the ECS agent. So that basically communicates with the Docker daemon locally on the machine and the state management engine on the back end of ECS, and effectively turns ECS API calls into Docker commands on all the instances in the cluster. So this agent is actually open source on GitHub, and you can kind of track our progress, submit bugs and issues, and we'll respond hopefully very quickly to those. But it's open source, so that's great. So you can take a look at the source code and kind of see how that's working on the back end. So to coordinate this cluster, we need a single source of truth for all the instances in the cluster. So we need to also know the containers that are running on those instances, what resources are still available, and we need to know about all the state changes, about all the containers that are running or that have stopped. So all this information together, we would like to refer to it as cluster state. And so ECS uses a distributed key value store that stores all of this cluster state. Because it's distributed, it brings some durability and scalability and high availability also. But it also makes doing things, just because it's a distributed system, it makes doing things like ensuring data is consistent, and it makes it more difficult to handle a lot of concurrent state changes for multiple clients. So we have to have a form of concurrency control in place that basically ensures that multiple state changes don't conflict. So for example, if a developer over here requests some resources, maybe all the remaining memory on a given instance in the cluster, and someone else over here does the same thing, only one of those requests can actually be fulfilled. And the other person would have to be told the request could not be fulfilled. So we have to do that very atomically, very quickly, at scale. So we can talk a little bit about how that is actually done. So the form of concurrency control we have, again, is one of Amazon's core distributed systems primitives. And that's significant, I think, because that's something we've used at scale in Amazon, and it's been proven to work very well at high scale for very, very large fleets. So we trust in that technology implicitly, and so we really value what ECS brings to customers there. But anyway, it's a Paxos-based transactional journal. If you're familiar with Paxos, it's quite difficult to implement. If you take a look at the paper for it, my mind usually melts. But in simple terms, it basically is a journal that keeps a record of every change made to a given data entry. And so a write to this data store is committed as a transaction in the journal with a specific order-based ID. So it might be a hash that's given to that particular write. So for the write to succeed, the proposed write must be the latest transaction since the last read. So that means you must have the latest data to update the journal. So if you make a read, and then subsequently a few writes happen before your next write, and you try to make a write based on what is now stale data, the write would fail for you. So this is the way that we can basically store cluster state with what's called optimistic concurrency control. And that's really ideal in environments where there's constantly changing data, there's a lot of clients, we have to make sure everything is atomically stored. So the end result is really high availability, low latency, and high throughput for this data store that can provide a consistent view for cluster state. And so all this neat stuff, all the ECS cluster management features, they're all exposed through a set of APIs here. And these API actions allow you to kind of build the basis for a set of solutions on top of Amazon ECS. So as an example, you might want to tie in your CI/CD solution. You might want to use Shippable or Jenkins. And these tools are able to kind of interact with ECS on your behalf just by using those APIs. Another maybe a little bit more esoteric example is you could totally build a custom scheduler. People are doing that. And they are doing that by just querying the APIs, understanding the state of the system, and making placement decisions based on what they're observing happening in the cluster. So schedulers can make decisions based on the data that we expose by APIs. And the way that works is each scheduler can basically query the state management system, understand what resources are available, and compare it to maybe the workload it needs to deploy, right? So the scheduler needs to find available resources, make a claim for those resources for a given workload, and then the scheduler basically updates the cluster state with those newly claimed resources, saying like, I own all the CPU on instance N, and the backend state management responds with an atomic transaction in the journal that says, yes, you have that, that is yours, no one else can take it from you. So if that resource is already claimed, ECS will reject that transaction because of the key value store maintaining that concurrency control. This is what we call, you'll hear us refer to it as shared state optimistic scheduling. So that means that all schedulers can see the current state of the cluster at all times. And it's the responsibility of that key value store to maintain consistency. So this is different from a pessimistic locking model in which given schedulers can only see a small portion of the resources available because the state manager on the back end will make offers based on what it thinks is appropriate for that scheduler to have. So here your schedulers can see the whole cluster all the time and make a resource claim and most likely get it because ECS should be maintaining what is available at any given time. So that's cool stuff. What are the actual benefits to you as a user? Let's walk through a few of those real quickly. So a huge benefit, I think, is that we hear from customers a lot that the difficulty of running containers at scale generally comes from installing and managing the cluster management software itself. That adds an operational burden that not everyone might be good at. And so it's kind of refreshing in some cases to not have to think about, are the management nodes up and running and responding? In this case, that component is all managed by ECS. So it really eliminates the need for any cluster management software. Again, it manages cluster state, containers, instances, and scaling, right? So you can start with just a single container or a single instance and scale that same cluster up to dozens or hundreds of containers and instances. To kind of support that notion that it scales very well, this is a demo we ran last year. Probably should do a new one at some point here. This is from mid-2015. But over 72 hours, we scaled our cluster to over 1,000 instances. And that is, the cluster size is represented by the purple line on this graph. And the other two lines are P50 and P99 response times for our APIs. We ran a bunch of list and describe APIs against the cluster. And what you can see here is that they're relatively flat, which demonstrates that ECS is very stable no matter the size of the cluster that it's managing. So that's really good for building predictable workflows around ECS. regardless of cluster size. We also built ECS with 2 built-in schedulers, and so we anticipate building more in the future and adding more features to the ones that exist right now. But right now, the 2 that exist there's a scheduler for long-running applications and services. Okay, so one that is responsible for making sure the workloads you have scheduled stay running and in the desired state you've configured. And there's also one that's for running short tasks like batch jobs, which is a lot less intelligent. It just kind of throws some resources at the cluster, waits for that job to complete, and then releases them again. So that custom scheduler I keep talking about, we'll kind of look at some of the APIs near the end, but you can see that in the describe cluster APIs, you can get a lot of information from the back end. And these same APIs, we use the same APIs for our built-in schedulers as you could use for a custom one. So that gives you a degree of flexibility when you want to schedule on ECS. Another benefit is that ECS is built to work with the AWS services you already probably use. And that will only increase in the future. The idea is to treat containers as first-class citizens. And so the way to do that is to provide additional features and integrations with other AWS services in the back end. So right now, you can use ECS with elastic load balancing. You can have it distribute traffic amongst your containers. You can attach EBS volumes to the instances in your cluster. You can configure the VPC for the instances in your cluster exactly as you would with regular EC2 instances. We have native support for CloudWatch logging, so you can log from your Docker containers directly into CloudWatch. We have support for IAM roles on the instances, so the containers can access the EC2 metadata service, just like any other application that you're used to on an instance. And then, of course, CloudTrail logging. If you're not using CloudTrail logging, shame on you. That is the first thing to do when you open up your AWS account. So that extensibility is really important because it helps us build a robust partner ecosystem around ECS. And so we have a number of logging and monitoring and CI/CD partners, service discovery partners that are really hooking into some of these APIs that ECS is providing to provide really tight integration. So this is one of the strongest things about ECS, I think, and I wish I could talk more about partner solutions. There's another talk that's Docker and ECS related that's kind of a microservices deep dive, and that talks a little bit about some CI solutions like Shippable, and it talks about Weave service discovery and how well all this stuff works with ECS and some cool demos. Unfortunately, not too much time for that in this talk. But also, the agent and the CLI are open source. The CLI that we're talking about here is the ECS CLI, which supports Docker Compose. So if you want to run Docker Compose on ECS and not have to write a task definition, which we'll look at in a second, you can use that. That particular project is being worked on at a higher pace these days, so we expect to see a lot of cool features coming out of that. And again, the open source agent is a nice feature. If you find some bugs in that, you can just report them on GitHub, which is great. So to sum up all of these features, rather than having to manage a set of machines that runs your cluster management software, much of that heavy lifting and housekeeping is abstracted behind a set of APIs, right? So it gives you the ability to run multiple tasks on a shared pool of resources. Looking at this particular graph, everything in orange is basically what runs behind the scenes on ECS itself. So that's the managed service component. And then the blue is what runs in your account, except for the internet, I guess. If you run the internet in your account, please use multi-AZ. Awesome. So the main components, again, just to reiterate, the key value store is what provides that consistency control. The cluster management engine keeps track of all of the state. The API allows you to interact with and query these two resources. And the agent communication service is what actually does the communication between all of the instances and the backend components in ECS. So now that we've talked about all the foundations for what allows ECS to run services for you, let's actually talk about running services. So this will be getting your applications into containers and distributed across the cluster. So the first thing to understand, the first primitive in ECS on the customer side, I suppose, is how you model your application. And that's using a file called a task definition. So this file basically contains a list of containers that you want to run in the same context. And in this case, a context is just a single instance. So everything that's deployed via task definition sits on the same instance. That's useful if you want to deploy like a web application, maybe a Flask application, and you always need a certain Nginx reverse proxy in front of it. You might define them in the same task definition. But it's also a very common approach to schedule a single container in a task definition and deploy that on its own to the cluster. A task definition supports a lot of the Docker concepts, like links, or logging drivers, or labels. And that stuff is kind of passed through the ECS agent to the Docker daemon, and that way your containers are spun up with all the configuration you need, and you've just defined it in the task definition. Task definitions also usefully are tracked by name and revision. So just like your source code or just like your containers, they are versioned artifacts that you can use to deploy your application and make changes, either rolling back or deploying new containers. So to create a task definition, you can use the console to specify which Docker image to use. You can also specify some resources like the memory and the ports, what volumes you want to use. You can specify environment variables. You can specify, as I mentioned, basically a majority of options for Docker flags. And you can pass them all through the task definition. And the essential flag here is interesting because that just specifies if that given container defined in the task should fail, then it should indicate that the whole task has failed. So you need at least one essential container in a task so that the ECS state engine can track if that one essential container has failed and if it should be restarted. Underneath, task definitions are JSON documents, which is, of course, very lovely. We do have, as I mentioned, a CLI that supports the Docker Compose project, and it kind of translates your YAML files into JSON. If you would like support for other formats, please let us know. We are interested in understanding what's best for customers in this case. So once you have a task definition rather, you can then schedule it onto a container instance. And once your task definition is created, a task is the running instantiation of a task definition. Now, there's a couple ways you can get it onto an instance. You can call the run task API. You can call the start task API. Those are a little bit different in that one is targeted to a specific resource. You can provide an argument for a container you want that task to land on. Or you can create a service, which is kind of a higher level construct, which we'll talk about in a second. And it kind of handles distributing it to multiple instances across the cluster for you. So as I mentioned, a task is an instantiation of a task definition. It's the core unit of work in ECS. And you really should just think about it as a grouping of related containers. It can be 1, it can be 10, but they just are what is actually running on the container instances. And you can run as many tasks on a given instance as will fit. So the scheduler will kind of take care of that for you. But you don't have to worry about the actual resource utilization on the instances so much. If the task won't fit, then the scheduler will find a different place to run it on the cluster. So the service scheduler is what we've built for long-running applications, and it has a lot of things built in that make it easier to manage services that should be running perpetually, right? And so that helps you maintain that uptime that you need to keep your app running and your users happy. So you reference a specific task definition, the number of those tasks you want to run, and then you can also configure an ELB that it should go behind, and the scheduler will launch the amount of tasks that you requested. You can also configure things like auto-scaling of these tasks. In the wizard, we'll go through that, and we'll look at what that entails. But it's similar to EC2 auto-scaling in that you can pick some metrics to monitor and to add more tasks to the service if those metrics are, if those alarms are breached. And so the scheduler is going to maintain the number of tasks you want to run, and it will also automatically load balance those tasks across availability zones. So it is availability zone aware, which is very nice. So if I schedule 4 and my cluster is across 2 AZs, I will get 2 and 2, which is a nice balance. So the auto-scaling is similar to the way we do auto-scaling with EC2 instances in the case that it is also AZ aware. So as long as you have an even number of tasks defined, you'll have an even number in each AZ. Otherwise, it'll do its best to kind of balance things in as close to equilibrium as it can get across 2 AZs. So scaling up is pretty simple. You can do it manually. You can do it automatically. You can do so in response to a number of different metrics. But what also is cool is you can update a service in a number of ways. So you can do a blue-green deployment or a rolling deployment style. So you can deploy the new version, and the scheduler will launch tasks with the new application version depending on your configuration. So you can define a maximum amount of containers that should be running at any given time and a minimum amount. So you can say that maybe I only want half of my old tasks to be terminated while I'm launching half of the new tasks at one time, and make sure that they gracefully roll out so I can maintain service availability for my users. Another nice feature is that the service scheduler will attempt to drain connections if you're using an ELB. It will wait for all active in-flight connections to drain before it terminates that container and removes it from an instance. And so the end result here is it just should be leaving the newest containers running. So have some time for a demo. It looks like actually I got plenty of time for demos. That's great. So let's switch over to my console here. Let's make sure this is actually still readable. And still connected. Great. So right now I have a cluster running. Excuse the funky name. It was spun up with CloudFormation. But right now it has one service running, which is a Redis container running in a service. It's a single Redis container right now. I'm using that as my persistence layer for my development project here. I have 3 container instances in this cluster, and we can see some information here about them in the ECS Instances tab. So we can see the version of the ECS agent and the Docker daemon that they are running, and we can see how much memory and CPU is available in any given instance. We can also click on it here to be taken to the EC2 console and see more specifics about it, and notice that it's a standard EC2 instance running in my account, which is great. So again, the task that is running here is called, this is my Redis task. It is named Redis, which is kind of relevant, which I'll explain in just a little bit. OK, so what I want to do is actually I have a front-end application that's a little Flask application that's going to interface with this Redis container, and I want to get that from my development machine to my ECS cluster. So what do I need to do here? I need to see if we can get to this. Can everyone see that OK? Cool. I didn't get any yeses, so I'm assuming no. All right. What do I have here? So let's get into my hit counter application here. And what do I have? So let's look at, Nano has nice colors, this application. So an interesting component of this application is on this line. I'm saying that or on the line below it actually, that my Redis host is just going to be named Redis. The reason I can just refer to it by service name is that I'm using Weave Service Discovery in the backend, so I don't have to worry about where it's running on my cluster. It just does unqualified name lookups across the whole cluster. So I can reference containers by name like I would locally with links across the whole cluster. So I've actually already built a container from this, but we can see that I have a Docker file, which is really straightforward. I start with a base Python 3.5 image from Docker Hub. I want to expose port 5000, and my command is basically running the gunicorn web server in front of my little Flask application. So I want to use EC2 container registry in this case, so let's take a look at the console and look at my repositories. And I've actually already built a repository for this one and pushed an image to it. But the interesting thing to look at, I'm kind of saving us some monotony in watching pushes and builds and the stuff that takes a while. But the useful thing here is that with ECR, you can get all of the commands you need to interact with a given repository from the console here, which is great. So it's actually nice to kind of demo what this git login command looks like. It's a little bit unintuitive. But let's get the login command here. And whoa. So it spits out a lot of information, which is a username and password. And this is a temporary token that is valid for only 12 hours. And we had to do that right now because we wanted to use IAM to authenticate to ECR. But that's not possible to do with Docker directly, so this is kind of our workaround for the time being. We do have a little Go binary you can point your Docker daemon to that will automatically refresh your credentials every time you do a Docker command that interacts with ECR. So that's a nice way of going about that, and you can find that on GitHub. It is not configured here because this is kind of the default way of using it. But we can build my demo container. So I'm in the directory with my Docker file, so we can build that. We can see it went really quickly because it's already built. But we can also say we want to tag this with the repository name, and let's call it version 1. All right, so if we do Docker images, we can see up here that I have this image tagged with a repository name and tag 1. And so if I want to push it to my ECR repository, I can go like this. Already exists in the repository again, much quicker than otherwise pushing a 500 meg image. But anyway, I want to go up here and I want to create a task definition. So let's look at my task definition here. And a couple of things to point out. So we have the command specified we're going to run. This is the same thing I specified in my Docker file. This is the command I need to run in the container. Above that is the image that I want to run. It's pointing to this demo app in my Docker Hub repository right now, but let's edit that and make it point to my ECR repository image. So let me go back. Let's grab this. Nano slow. So I need to, there we go. So my task definition has been registered, and where is the task definition ARN? So here's my ARN. So let's go back to the console, and let's take a look at that particular task. So my Santa Clara Summit right here, this is the one we just pushed. So we can go in here, and we can see that the image it's pointing to is the one in my ECR repository, and we can create a service from it. So we're going to deploy it on the Santa Clara Summit cluster here. We'll just call it demo service. Say I want 3 of these. And these are some of those deployment rollout options I was talking about. So this is how you configure like a rolling or a blue-green deployment, kind of by playing with some of these values. Some of the more important stuff to do here is configure an ELB. So let's grab the ELB that I have built for this. It's already configured to point towards port 5000 on the container. We'll go ahead and save that. And let's configure autoscaling as well. So we'll configure to adjust the service's desired count in the event of certain alarms being breached. So we'll say we want 1 at the minimum. Let's say we want 6 at the maximum. And here's where you can configure the CloudWatch alarms. So I've already configured a couple. Let's say we scale out with high CPU. So when I have greater than 50% CPU utilization across the service for a minute or more, let's add 1 task. And then for my scale down policy, we'll do something a little bit similar here. When CPU is below 20% across the whole service for 5 minutes, we'll remove 1 task. So here we go. Let's create that service. And we will kind of watch this work here. So in the meantime, what I actually want to do, after I make sure this works in my development process, I want to move my persistence layer to something not in a container. Just a personal preference. So what I have over here is I have a Elasticache Redis cluster. And let's go ahead and build a new container. Let's modify my app, and let's point it to one of these Elasticache nodes. So let's look at this node. Let's copy this node endpoint. Let's switch back over here. And where are we? So let's get this hit counter. Let's edit this host connection string for Redis. Pop in my Elasticache. Oops, that did not copy. See, do I have it now? Great. Cool. So we can see that I have the Docker file again. We don't have to change anything else. We'll call it, what did I call it before? It's rebuild this. And let's go back to my ECR registry, and we can get those commands again in case I forgot them. So we can view my push commands. So we can tag it again. We'll call it version 2. Latest isn't a version. And then let's push that up. There we go. So it's quick because it only has to push a single layer. I made a small change. All of the rest of it already exists in my repository. And cool, so we're staged there. So let's go back and look at our cluster and see if our service is actually running now. So we have 4 tasks running. That's great. Let's look at this front-end demo service. Let's take a look at the load balancer. So let's pop that open in the EC2 console. Grab that DNS name. Cool. So it's our little hit counter application, and it's interacting with Redis on the back end. So that's great. But what do I want to do now? So actually, I don't have to go through the whole process of creating a new service. In this case, I can just update the service. So what I want to do is go from this. Where is it? Oh, I didn't create a task definition from it, did I? That's what I missed. So let's go to here. Let's look at my, that's what it is. Let's nano this task definition. Let's go over here. That's a 2. Great. So now we have a second version of demo 2. And I'm losing my mind, apparently. Let's look at task definitions. Oh, that's why. No worries, just losing my mind. So here we go. Let's go back, edit that service. This is the one we need. So let's go ahead and update. Let's roll this out. And we can watch the deployment happen here. So we can see that we have 3 of the old version running. We desire 3 of the new one, but nothing has happened yet. It is not pending or running yet. So we're just going to wait for that deployment to happen here. And in the meantime, we can actually go ahead and we can scale down the service that we are running. Let's see. With the Redis container, because I no longer need that. So let's update this one. Let's go ahead and scale it down to 0. And let's update that. So looking back at the cluster, what do we have running now? So I have my new service running. Let's take a look at the load balancer. And let's see if it is now interacting with my Elasticache cluster. And we'll know it is because it doesn't have any sort of hit counting. It should be completely fresh and at 0. And probably a little bit aggressive with getting that to roll out. There we go. So the new one is running. Beautiful. So with a little bit of problems doing that manually, as you can see, it's not the smoothest experience. If you're doing it manually every time, it can be a little bit time consuming. But you can do it manually. And the idea is to kind of illustrate that workflow from container to task definition to service. And the way that we generally see customers doing this workflow, though, is via a CI system. So every time when you want to update your code, you'll basically commit code to a GitHub repository. You can use a webhook to kick off a Docker build, either from one of our CI partners or in something like Docker Hub directly. Build that new container, and then have your CI service automatically update your task definition with the new container revision. In many cases, they'll also update your running services with that new task. So all you have to do is commit to a GitHub repository if you've configured this correctly, and a CI system can deploy it all the way to ECS, either in staging or production for you. And that's a little bit of the demo that's shown in the microservices deep dive session. So if you're interested in that sort of workflow, take a look there. So I have a little bit of time here at the end. I'm going to hang out up front for some questions, some Q&A. So come talk to me. I'd love to hear your questions. Thank you very much.